When NASA announced that Voyager 1 had left the solar system, it was one of the biggest science headlines of the decade. Newspapers ran it, television ran it, social media ran it. The story was clean, dramatic, easy to understand. A spacecraft launched in 1977 had finally crossed the final frontier and entered the space between the stars. Except there was a problem. It was not quite true. Voyager 1 had done something extraordinary, but what it actually did was stranger, more complicated, and far more interesting than any headline captured. And understanding the distinction between what the headline said and what actually happened is the only way to understand what Voyager 1 has truly been doing out there, alone in the dark, for more than a decade. Before we get started, if this kind of deep science is what you come here for, take a second to subscribe or leave a like. It helps this channel reach more curious minds. Now, let us begin. On the 12th of September 2013, NASA held a press conference. Project scientist Ed Stone stood before the assembled journalists and announced that Voyager 1 had crossed the heliopause, the boundary where the solar wind stops, and entered the interstellar medium. The confirmation had taken 13 months of analysis after the actual event because the evidence had been ambiguous and the scientists were careful. Stone chose his words with precision. He said Voyager 1 had entered interstellar space. He did not say it had left the solar system. The headline said something different. They took the phrase interstellar space and translated it into language everyone understood. They said Voyager 1 had left the solar system. It was a shorthand. It was not malicious. It was journalists reducing a nuanced scientific statement to something that would fit on a front page. But in the translation, something important was lost. When people say Voyager 1 has left the solar system, what they usually mean is that it crossed the heliopause, the boundary where the solar wind stops. That is a real and significant boundary. It is the edge of the direct influence of our star, the point where the stream of charged particles the star has been firing into space for billions of years finally runs out of momentum and stops. Voyager 1 crossed that boundary on the 25th of August, 2012. That part of the story is entirely accurate. But the solar system does not end at the heliopause, not even close. Beyond the heliopause, extending outward to somewhere between 40,000 and 100,000 astronomical units from our star, that is 1 to 2 full light-years, orbits the Oort cloud. Roughly 1 trillion icy bodies, left over from the formation of the solar system, circling our star in an enormous spherical shell. Every long-period comet you have ever seen photograph the ones with tails that blaze across the night sky once in a human lifetime came from the Oort cloud. Those objects orbit the star. They are gravitationally bound to it. By any reasonable definition, they are part of the solar system. Voyager 1 is currently about 172 astronomical units from the star. The inner edge of the Oort cloud begins somewhere around 2,000 astronomical units. Voyager will not reach that inner edge for roughly 300 years. It will not clear the outer edge for tens of thousands of years. By the time it does, every instrument on board will have been silent for millennia. There is a scale comparison that makes this visceral. Imagine you are standing in the center of the continental United States and you want to reach the Pacific Ocean. Walking 3 miles west brings you closer to the Pacific, relatively speaking, than Voyager 1 is to the true gravitational edge of the solar system. In cosmic terms, Voyager has barely taken its first step out of the front door. So what did Voyager 1 actually cross? It crossed the heliopause. It entered the interstellar medium, the extraordinarily thin mist of gas, dust, and magnetic field that fills the space between stars. That is not a small thing. It is a remarkable thing. But it is not the same as leaving the solar system. And the distinction matters, because what Voyager is measuring out there, what it has been measuring for more than a decade, is something far more specific, far more local, and far more strange than the phrase interstellar space implies. Understanding the Oort cloud properly changes the picture entirely. The cloud was not discovered by direct observation. No telescope has ever imaged it. It was inferred by a Dutch astronomer named Jan Hendrik Oort in 1950 from the behavior of long-period comets arriving in the inner solar system. He noticed that these comets were arriving from all directions, equally not concentrated in the plane of the solar system like the planets and asteroids, but distributed across the entire sky. And they were arriving on orbits with periods of millions of years, suggesting they came from a vast, roughly spherical reservoir at enormous distance. Oort calculated where that reservoir had to be based on the orbital dynamics of the comets he observed, and his model has held up for 7 decades. We have never photographed a single object in the Oort cloud directly. We know it exists because of what it sends toward us. The Oort cloud itself is thought to have formed from objects that were originally part of the protoplanetary disk around our young star, the same swirling cloud of gas and dust that eventually coalesced into the planets. Early in the solar system's history, gravitational interactions with the forming giant planets, particularly Jupiter and Neptune, flung vast numbers of these small bodies outward. Some escaped the solar system entirely. Others were scattered into highly elongated orbits reaching into the distant cloud, where the gentle gravitational tugs of passing stars and the galactic tidal force kept them in a loose, slowly drifting swarm. Every so often, one of these ancient objects is nudged by some perturbation, a passing star, a denser-than-average region of the galaxy, a change in the galactic tide, and falls inward on a long journey toward the inner solar system, eventually becoming the bright comets that have astonished human observers throughout recorded history. They are messengers from a reservoir we have never seen, returning after millions of years in the dark. The Oort cloud is not the only evidence that our star's gravitational reach extends far beyond what we typically think of as the solar system. In 2003, astronomers discovered an object called Sedna, a reddish body about 3/4 the diameter of Pluto, orbiting the star on an extraordinarily elongated path. At its closest, Sedna approaches to about 76 astronomical units. At its furthest, it travels out to around 937 astronomical units. It never comes anywhere near the established planets. Its orbit takes approximately 11,400 years to complete. And it is almost certainly not alone. Astronomers believe Sedna is one of the closer members of what may be a vast population of objects in the inner Oort cloud, occupying the space between the outer planets and the main cloud structure. These objects have likely been there for the entire age of the solar system, slowly circling on orbits so elongated they spend most of their time in a region no instrument has ever visited. If you want to know exactly where the solar system ends in a gravitational sense, the answer involves the Hill sphere, the theoretical boundary within which the star's gravity is the dominant attractive force, beyond which another star's gravity or the overall tidal pull of the galaxy would overwhelm our star's hold on any orbiting object. That boundary extends to roughly 2 light-years. The Oort cloud fills most of that space. Everything within 2 light-years of our star, unless it is moving fast enough to escape entirely, belongs here. Voyager 1 is at a tiny fraction of that distance. It is inside the solar system by every gravitational measure that matters. Beyond the Oort cloud, there is nothing gravitationally bound to our star. Only then does the solar system truly end. Voyager 1 has not reached that boundary. It has entered the interstellar medium, which begins at the heliopause, but it is still well within the gravitational sphere of influence of our star. The boundary it crossed was physical and magnetic, not gravitational. These are different things. They happen at different distances, and the region Voyager now inhabits in between the heliopause and the inner Oort cloud is what makes the mission so scientifically extraordinary. Nobody had ever put instruments there before. There is one more piece of context that almost never gets included in the popular telling of this story, and without it, the significance of what Voyager is measuring is impossible to fully appreciate. Our star is moving through the galaxy at roughly 43,000 miles per hour relative to the local standard of rest. It has been moving for 4.5 billion years, carving out the heliosphere as it goes, pressing outward against whatever interstellar material surrounds it. The material it is currently pressing against the plasma, the magnetic field, the thin gas that defines its immediate neighborhood occupies a structure astronomers call the local interstellar cloud, sometimes called the local fluff. It is a warm, partially ionized pocket of gas roughly 30 light-years across. Our star entered this cloud somewhere between 44,000 and 150,000 years ago. The estimate is uncertain because cloud boundaries are not sharp and the relative motion is complex. But somewhere in the deep past, sometime during the last ice ages on Earth or somewhat before, our solar system moved into this particular pocket of gas. The local interstellar cloud is not generic interstellar space. It has a specific temperature around 6,000 Kelvin, hot enough to be partially ionized, cool enough for neutral hydrogen to survive alongside the plasma. It has its own magnetic field orientation, its own density profile. It is moving relative to the surrounding interstellar medium at around 15 miles per second. It is carrying our solar system with it as it drifts, and we are being carried through it at the same time. At some point in the future, possibly within a few thousand years, possibly longer, we will exit the cloud and enter whatever region lies beyond. What that region is like, and how that transition will affect the heliosphere, is one of the questions Voyager's data is beginning to let scientists think about quantitatively for the first time. Voyager 1 is not sampling generic interstellar space. It is sampling the inside of this specific cloud, the local fluff, from a position never before occupied by any human-made instrument. Every reading it takes is a direct measurement of the specific environment our solar system currently inhabits, a region whose influence on the heliosphere, and therefore on the cosmic ray shielding of the inner planets, extends back tens of thousands of years and will continue for tens of thousands more. What happens when the solar system exits the local interstellar cloud is not a small question. The cloud ahead of us in the direction our star is moving is called the G cloud. It is denser and slightly cooler than the local interstellar cloud we currently inhabit. If our solar system moves into the G cloud within the next few thousand years, the heliosphere will likely be compressed by the higher external pressure. A compressed heliosphere means a smaller protective bubble around the inner planets. More galactic cosmic rays reaching the inner solar system. Not necessarily a catastrophe. The change would unfold over thousands of years, not centuries, but a genuine alteration to the radiation environment experienced by every living thing on Earth's surface. Scientists have only been able to begin modeling these transitions quantitatively because Voyager 1 provided the first direct measurement of the interstellar medium's properties from inside it. Before that, the numbers going into the models were estimates. Now, for this one specific cloud, they are measurements. Here is something that rarely gets mentioned. The journey from the termination shock to the heliopause took 8 years. Voyager 1 crossed the termination shock in December 2004 at 94 astronomical units. It crossed the heliopause in August 2012 at 121.7 astronomical units. In between, across roughly 28 astronomical units of space, roughly 2.5 billion miles of distance, it was traversing the heliosheath. That region between the outer boundary of the supersonic solar wind and the heliopause itself. 8 years of flight through a zone that models had described as a relatively straightforward transition region, and that turned out to be anything but. Inside the heliosheath, the solar wind is no longer supersonic. It has been slowed and compressed by the termination shock, and the plasma piles up, pushing against the heliopause from the inside like air pressing against a balloon. The magnetic field here is folded into a series of enormous magnetic bubbles, some as large as 1 billion miles across. As the solar wind's spiraling magnetic field is tangled and compressed into loops by the turbulent dynamics of the heliosheath. Voyager 1 moved through this region for 8 years, detecting particle populations that oscillated, magnetic fields that fluctuated, and structures nobody had predicted. Among them was the stagnation region around 113 astronomical units, a zone 8.6 astronomical units across where the outward velocity of the solar wind dropped to 0. And then the magnetic highway, and then the heliopause itself. The crossing was not a sudden arrival at a well-defined wall. It was the culmination of 8 years of increasingly strange physics, each new region more unfamiliar than the last. Now consider what it means to try to measure this environment directly. Before Voyager reached the heliopause, everything scientists knew about the interstellar medium was deduced from remote observation. They analyzed the way interstellar gas absorbs certain wavelengths of light from distant stars. They measured the time delays in radio signals arriving from pulsars. They tracked the spectra of ionized gas clouds across the galaxy. They built elaborate theoretical models of the interstellar medium from these indirect signals, corrected them with new observations, debated them in journals for decades. All of this knowledge was gathered from inside the heliosphere, looking outward through the solar bubble at a region the solar bubble itself was preventing them from reaching. That situation was always going to have a fundamental limit. At some point, the only way to know what was on the other side was to send something there. And the only thing we had ever sent in the right direction, the only objects that had ever been on a trajectory that could actually cross the heliopause, were the two Voyager spacecraft, and their predecessors Pioneers 10 and 11, which were less sensitive and whose power systems died before they could reach the boundary. Here is something that almost never gets mentioned. Voyager 1 was very nearly unable to confirm its own crossing. The instrument that was supposed to provide the definitive evidence, the one designed to measure plasma density directly, to sample the electron content of the surrounding space the way a thermometer samples temperature, stopped working in 1980. It failed during the Saturn flyby, 2 years into the mission. That was 12 years before the cameras went dark, 32 years before the heliopause crossing. The plasma science instrument was supposed to be the first thing to register the change as Voyager crossed into the interstellar medium to record the moment solar wind plasma was replaced by the thicker, colder interstellar plasma on the other side. Without it, the crossing had to be inferred from secondary signals, indirect evidence, and a great deal of careful analysis. 13 months of uncertainty followed what turned out to be the most historic boundary crossing in the history of spaceflight. The story of what caused the plasma instrument's failure is itself a small portrait of the risks of deep space exploration. During the Saturn flyby, a software command sent to manage data collection on other instruments inadvertently affected the plasma instrument's electronics. The exact sequence of events is disputed, and the full technical account runs to dozens of pages. The short version is that a decision made to capture better scientific data from one instrument contributed to the permanent incapacitation of another. Nobody intended this. The teams were dealing with a level of complexity that no simulation had fully anticipated. The instrument had been designed to work for 4 years. By the time of its failure, it had already exceeded expectations. But losing it meant that when Voyager 1 finally crossed into interstellar space 32 years later, scientists would have to piece together the evidence from what remained rather than reading it directly from the instrument specifically designed for the purpose. What remained, after the plasma instrument was gone and after years of additional shutdowns, was 4 instruments still alive at the time of the crossing. The first is the cosmic ray subsystem. It counts high-energy particles, particles accelerated to near-light speeds by supernova explosions across the galaxy. Particles that carry energies billions of times greater than those produced in particle accelerators on Earth. These galactic cosmic rays filter through the interstellar medium from their distant sources and push against the heliopause from outside. Inside the heliosphere, the solar wind deflects and scatters many of them outward. The cosmic ray subsystem measures how many get through. When Voyager crossed the heliopause, cosmic ray counts tripled almost immediately, a permanent step increase that told scientists Voyager had entered a region where the solar bubble was no longer blocking these particles. The measurement was unambiguous, unprecedented, and irreplaceable. No other instrument in history had ever directly compared the cosmic ray environment inside and outside a heliosphere. The second is the low-energy charged particles experiment, a complementary detector that measures particles at lower energies, including solar wind protons and electrons, and the lower energy component of cosmic rays entering from outside. While the cosmic ray subsystem focuses on the most energetic galactic particles, this instrument tracks the lower energy population and the transition between solar particles and interstellar particles across the heliopause. Together, the 2 particle detectors gave scientists the first direct measurement of the particle populations on both sides of the boundary simultaneously. And that comparison produced one of the mission's most important numbers. The heliosphere blocks more than 70% of galactic cosmic radiation from reaching the inner solar system. That number deserves to stand on its own for a moment, because its implications reach far beyond the heliopause measurement itself. Galactic cosmic rays originate from supernova explosions across the galaxy. When a massive star dies and its core collapses, the resulting shock wave accelerates particles, mostly protons and heavier atomic nuclei, to extraordinary energies, often approaching the speed of light. These particles then travel through the interstellar medium for thousands or millions of years before arriving in our neighborhood. The heliosphere deflects most of them. Before Voyager, the magnitude of this shielding was estimated. After Voyager, it was measured. The number was 70%. 3 out of every 10 galactic cosmic ray particles that approach the heliopause get through. The other 7 are turned away. What would change if that number were different? If the heliosphere were smaller, compressed by a denser interstellar cloud, or reduced by a period of lower stellar activity, more cosmic rays would reach Earth's surface. Cosmic rays ionize atoms in the atmosphere and produce secondary particles that reach the ground. At higher flux levels, the rate of DNA double-strand breaks in living tissue would increase. Over geological timescales, the cumulative effect on mutation rates and evolutionary trajectories is not negligible. Some researchers have proposed that episodes of increased galactic cosmic ray exposure in Earth's history may correlate with events in the fossil record: elevated extinction pressures, accelerated evolution, possible climate effects from cosmic ray-induced cloud nucleation. These hypotheses are debated and not established. But they are now tractable scientific questions precisely because Voyager gave us the 70% baseline to build from. The implications extend outward as well. Every star with an active stellar wind has its own heliosphere, equivalent an astrosphere. The size and shielding effectiveness of that astrosphere depends on the star's wind strength and the properties of the interstellar medium it is moving through. A planet in the habitable zone of a red dwarf, a small, dim star with a relatively weak stellar wind, might orbit inside an astrosphere that blocks considerably less than 70% of galactic cosmic radiation. That planet might receive 2 or 3 times more cosmic ray flux than Earth does. Whether that additional radiation would prevent complex life from developing, or simply change its trajectory, or have no meaningful effect, is an open question. But it is now a quantitative question, because Voyager gave us the number to compare against. The search for habitable worlds around other stars now has one more variable to consider, and we have Voyager's cosmic ray telescope to thank for making it measurable. While Voyager was crossing the heliopause in the early 2010s, a smaller, cheaper satellite was mapping it from inside without ever leaving Earth orbit. The Interstellar Boundary Explorer, known as IBEX, was launched by NASA in 2008. It orbited Earth but pointed its detectors outward, toward the heliopause, detecting a specific kind of particle called an energetic neutral atom. These particles are formed at the heliopause when fast-moving solar wind protons steal electrons from slower interstellar hydrogen atoms. The newly neutral particle, now invisible to magnetic fields, travels in a straight line back through the heliosphere toward Earth. By mapping where these particles were arriving from, IBEX could construct an all-sky image of the heliopause from tens of billions of miles away, a remote portrait of a boundary that Voyager was crossing in person. What that portrait revealed in 2009 was not what anyone expected. Across the forward face of the heliosphere, the face pressing into the direction of the solar system's motion through the galaxy, there was a bright, narrow ribbon of unusually intense particle emission, an arc of concentrated signal cutting diagonally across the sky. Nothing like it had appeared in any model. Nobody had predicted it. Scientists spent years developing competing explanations. The leading interpretation is that the ribbon marks the region where the local interstellar magnetic field is oriented precisely perpendicular to the direction back toward our star, a geometric sweet spot where the interaction between the solar wind and the interstellar field produces a locally elevated flux of neutral atoms heading back toward Earth. The ribbon is, in effect, a map of the interstellar magnetic field direction painted on the inside of the solar system's boundary. IBEX also reported that the heliosphere has no bow shock. Earlier models predicted that as our solar system plows through the interstellar medium at roughly 14 miles per second, it should generate a standing shock wave ahead of it, like the pressure wave that builds ahead of a supersonic aircraft. IBEX found no evidence of one. The interaction between the heliosphere and the interstellar medium turns out to be gentler than that, more like a blunt body pushing through a slow current than a supersonic object creating a sonic boom. The interstellar medium, despite its magnetic field being twice as strong as expected, is not dense enough to produce a bow shock at the speed our solar system moves through it. One more confident prediction, quietly withdrawn. The third is the magnetometer. Tiny, extraordinarily sensitive, measuring magnetic field strengths measured in nanotesla's billionths of a Tesla, it tracks the direction and intensity of the magnetic field surrounding the spacecraft as it moves. The magnetometer produced some of the most controversial and surprising data of the entire crossing. Models had predicted that the magnetic field direction would rotate sharply at the heliopause, shifting from the direction imposed by the star's field to the direction of the galactic field. When no rotation happened, when the field direction changed by only about 2 degrees, the scientific community spent months debating whether the crossing had really occurred at all. The answer, eventually, was that the local galactic field happened by cosmic coincidence to point in nearly the same direction as the solar field at the precise location where Voyager crossed. The magnetometer that failed to rotate was still right. It was the prediction that was incomplete. The fourth instrument, the one that ultimately provided the decisive evidence for the crossing, and has gone on to produce some of the most remarkable scientific results of the entire mission, is the plasma wave subsystem. It consists of 2 antennas, each roughly 30 feet long, extending behind the spacecraft like an enormous pair of ears. These antennas are not listening for radio signals from alien civilizations. They are listening for the vibration of electrons in the plasma surrounding the spacecraft. When a pressure wave moves through plasma, it causes the electrons to oscillate at a frequency that depends on how densely packed they are. Measure the frequency of that oscillation, and you can calculate the density of the plasma. The plasma wave subsystem was designed to detect these oscillations in the environment around Jupiter and Saturn. It was never specifically intended to measure the interstellar medium. But it was still working when Voyager got there, and in the absence of the plasma instrument, it became the most important scientific tool the mission possessed. Think about the history of that instrument. It was designed in the early 1970s using technology that no longer exists in any active form. It was built for a 4-year planetary mission to the outer solar system. By the time it detected the hum of interstellar plasma, it had been operating for 35 years in a temperature environment not far above absolute zero, maintained by heaters running off power generated by the radioactive decay of plutonium in generators that had themselves been operating continuously since launch. The engineers who built the instrument were mostly retired or dead. The technology that built it was obsolete. The spacecraft carrying it had outlived 3 generations of the people who first designed it. And those 2 30-foot wires were still vibrating in the dark, still registering the faintest whispers of plasma oscillation from a medium nobody had ever directly measured. Consider what the instrument saw when it finally got there. In November of 2012, 3 months after the crossing, the plasma wave subsystem detected the first sounds of interstellar space. Scientists converted the plasma oscillation data into audio not because there is literally sound in space, but because the oscillation frequencies fall within a range that human ears can process. What emerged when they played it back was a faint, rising hum. The sound of electrons vibrating in the thin plasma between the stars converted into something a human being could hear for the first time in history. Think about what that moment actually represented. For the entirety of human civilization until August 2012, every measurement of the interstellar medium was remote. We inferred its properties from the way it absorbed starlight. We estimated its density from the travel times of radio pulses from distant pulsars. We guessed at its magnetic field by tracing how it deflected cosmic rays. Everything was deduction. Everything was inference collected from inside the solar bubble and aimed outward at a region the bubble itself was blocking. On the 9th of April, 2013, when the plasma around Voyager 1 began to vibrate in response to a pressure wave that had originated at the star months earlier, everything changed. An instrument was immersed in the interstellar medium, reporting back from inside it, measuring it directly the way a hydrometer measures the salinity of the water it is submerged in. The era of remote sensing of the interstellar medium ended. The era of direct measurement began. It began with a hum. That first measurement revealed something striking. The plasma density in the interstellar medium was more than 40 times higher than the plasma density in the outer heliosheath Voyager had just left. The models had predicted a density increase at the heliopause, but the magnitude confirmed exactly where the spacecraft was. It was in the interstellar medium. The solar bubble was behind it. And the plasma wave subsystem was the instrument that confirmed it, 13 months after the crossing actually happened, by detecting an oscillation in interstellar electrons caused by a pressure wave that had left the star before Voyager had even finished crossing the boundary. The density jump did not stay constant. That was the first major surprise. As Voyager 1 traveled deeper into the interstellar medium over the following years, scientists noticed the plasma density was rising. Not dramatically, not in sudden jumps, but steadily and consistently. The medium was getting denser the further the spacecraft traveled from the heliopause. This was unexpected. Models had assumed a fairly uniform interstellar medium in the immediate neighborhood of our star. What Voyager was measuring instead was a gradient, a rising density that implies some kind of spatial structure in the local interstellar cloud, a variation in how the gas is distributed across the region just outside the heliosphere. In 2021, a researcher named Stella Acher, then a doctoral student at Cornell University, was sifting through Voyager 1's plasma wave data, looking for weak signals buried in the noise. Scientists had known that the plasma wave subsystem could measure interstellar plasma density when solar pressure waves passed through, but those events were rare, perhaps once a year. Between them was silence. Acher was looking for a different kind of signal, one that was always there, independent of solar activity. What she found changed the picture entirely. Buried in years of data, starting around mid-2017, was a faint, nearly continuous oscillation. Not the dramatic surges caused by solar outbursts. Not the abrupt whistles that appeared when a pressure wave swept past. Something quieter and more persistent a tone, barely above background noise, that was present in almost every data sample she examined and continued through all the data she analyzed through 2020. As the frequency of this tone drifted slowly up and down over months and years, it was tracking the density of the interstellar plasma around the spacecraft in something close to real time. Acher described it plainly. It is very faint and monotone because it is in a narrow frequency bandwidth. We are detecting the faint, persistent hum of interstellar gas. Her supervisor, James Cordes, offered the most poetic description. The interstellar medium is like a quiet or gentle rain. In the case of a solar outburst, it is like detecting a lightning burst in a thunderstorm, and then it is back to a gentle rain. What the discovery gave scientists was something they had never had before, a continuous, running measurement of interstellar plasma density that did not depend on waiting for the star to provide a trigger. Shami Chatterjee, a co-author on the paper, said it directly. We have never had a chance to evaluate it. Now we know we do not need a fortuitous event related to the star to measure interstellar plasma. Regardless of what the star is doing, Voyager is sending back detail. For the first time, the very local interstellar medium could be monitored in something close to real time, from inside it, over a baseline of years. Based on the signal, electron density around Voyager 1 had started rising in 2013 and reached its then current level around mid-2015, a roughly 40-fold increase in density compared to the plastrain, blanks and 5.7 heliosheath readings just before the crossing. The spacecraft appeared to be in a similar density range, with some fluctuations, through all the data Acher analyzed. The map of the interstellar medium's density that this continuous signal enabled is the most detailed such map ever assembled for any region of space outside the heliosphere. The plasma density was not the only number that confounded expectations when Voyager finally reached the other side. The magnetic field did too, and in a way that senior scientists described, without exaggeration, as requiring 60 years of assumptions to be discarded. Before the crossing, the expected strength of the interstellar magnetic field was estimated at roughly 2.5 microgauss. This was not a guess. It was the product of decades of careful astronomical measurement and theoretical modeling observations of how the galactic magnetic field aligned with gas clouds, how it influenced the shapes of distant nebulae, How it deflected the paths of cosmic rays arriving from distant supernova remnants. 2.5 microgauss was the consensus figure. It was in the textbooks. It was the number that every model of the heliosphere used when calculating the balance point between the outward pressure of the solar wind and the inward pressure of the interstellar medium. When Voyager 1 crossed the heliopause and its magnetometer began measuring the field on the other side, the reading was 5 microgauss, twice the consensus prediction. When Voyager 2 crossed in 2018 and made its own independent measurement from a completely different direction, it found 7 microgauss, nearly 3 times the textbook value. A magnetic field twice as strong as the models assumed does not simply revise a number in a table, it changes the shape of everything. The heliosphere is formed by the balance between two pressures, the outward push of the solar wind and the inward push of the interstellar medium, including its magnetic field. If the interstellar field is twice as strong as the models assumed, that balance point shifts inward. The solar bubble cannot expand as freely. Its shape is more constrained. The rounded, roughly symmetric sphere that appeared in every textbook diagram and documentary for 60 years is not what the heliosphere actually looks like. It is compressed by a field twice as powerful as anyone accounted for, flattened in ways the models did not predict, and shaped by the magnetic pressure of the interstellar medium in ways we are still working to understand. One of the Voyager mission's senior researchers described it without hedging. For 60 years, we had the wrong image of the heliosphere. Not approximately right. Not close enough for practical purposes. Wrong. The interstellar magnetic field pushing against the solar bubble is far stronger than generations of space physicists had calculated, and that single measured fact, 2 microgauss versus 5, or 7, overturns the foundational assumption that every heliosphere model was built on. The stronger field also has direct implications for life on Earth. The size and strength of the heliosphere determines how much galactic cosmic radiation, high-energy particles from supernova explosions across the galaxy, reaches the inner solar system. A stronger interstellar magnetic field means a compressed heliosphere. A compressed heliosphere means slightly less shielding. The connection runs from the magnetic field measurement in Voyager's instruments all the way to the surface of the Earth, where cosmic rays register in every living cell's DNA repair mechanisms. It is a long chain of causation. But the chain is real. The measured fact is at one end of it, and we are at the other. There is something quietly elegant about the way the interstellar medium and the heliosphere interact that the raw science captures but does not always express. Our star does not simply press outward against the interstellar medium and stop. It echoes. Every significant eruption from the star, every coronal mass ejection that launches billions of tons of plasma outward at millions of miles per hour eventually reaches the heliopause and does not simply stop there. The pressure pulse passes through the boundary and propagates outward into the interstellar medium as an acoustic wave, compressing and disturbing the thin plasma on the other side, traveling outward for months or years after the solar particles themselves were stopped at the boundary. Voyager 1 detects these waves. They arrive as plasma oscillation events, those abrupt whistles in the data that the plasma wave subsystem registers. A solar event occurs on the star, a year or more passes. The pressure wave crosses the entire heliosphere, hits the heliopause from the inside, launches an acoustic shock into interstellar space, and arrives at Voyager 1's location, the antenna's ring. Scientists measure the oscillation frequency. They calculate the plasma density. They trace the wave backward through the timeline and find its origin in an eruption that happened at the star more than a year before. The star's own voice, compressed and transformed by the heliopause, echoing through the interstellar medium and still detectable from a machine that crossed the boundary months or years after the eruption that generated it. This is also how the crossing itself was finally confirmed. The coronal mass ejection from March 2012, the one whose echoing pressure wave reached Voyager in April 2013 and finally provided the density measurement that confirmed the heliopause had been crossed, that was the star providing its own evidence. The instrument that should have confirmed the crossing immediately was broken. The instrument that confirmed it 13 months later did so because the star itself sent a messenger. It is one of the stranger and more beautiful coincidences in the history of exploration. A machine built to survive a 4-year planetary mission, still listening in interstellar space after 35 years, detected a wave generated by the very star it had left, and that wave was the proof that the leaving had happened. In 2020, something changed in Voyager 1's data that has not yet been explained. The magnetometer registered an abrupt jump in magnetic field intensity. The plasma wave subsystem registered an elevated density simultaneously. Both readings rose above their previous baseline in a way consistent with what had happened before pressure waves from the star, passing through and dissipating after a few months. Scientists noted the anomaly and waited for it to return to baseline. It did not return to baseline. The elevated field intensity and the elevated plasma density persisted through 2021, through 2022. Through the period in 2022 when the spacecraft suffered a serious computer malfunction and scientists spent months unable to properly interpret its instrument data. When telemetry was restored and the data cleared, the anomaly was still there. Something had changed in the interstellar environment around Voyager 1, and it was not going away. One leading hypothesis comes from a researcher named Adam Szabo at NASA's Goddard Space Flight Center. Szabo proposed that Voyager 1 may have entered a small ancient cloud of interstellar plasma, a pocket of material carrying a distinctly different magnetic field signature from the surrounding interstellar medium. If this cloud originated from the magnetic bubble around another star, expelled by some energetic event long ago, and has been drifting through the local interstellar cloud for millions of years, then Voyager 1 would not simply have entered a pocket of denser interstellar gas. It would have entered material that was once under another star's influence. Material that carries another star's magnetic imprint, still preserved in the cold of interstellar space millions of years after it left its source. That would make Voyager 1 the first human instrument to directly sample material that was once part of another star's environment. Not material from between the stars, material from another star itself. Carried across the galaxy by time and drift, encountered by accident when a decades-old spacecraft happened to cross its path. This theory has not been confirmed. There are other explanations. A very large, slow-moving pressure wave from our own star remains a viable alternative. But the anomaly is real, the data is being actively studied, and the fact that this is a live scientific controversy in journals and at conferences right now, argued over by specialists using data from a spacecraft transmitting on 23 watts of power across 25 billion kilometers of space, is one of the more extraordinary facts in contemporary science. The technical story of how Voyager 1 has survived long enough to gather all of this is almost as remarkable as the science itself. Power comes from 3 small generators on each spacecraft, converting heat from the natural decay of plutonium-238 into electricity. At launch, each Voyager generated about 470 watts, barely enough to run a handful of incandescent bulbs. Every year, as the plutonium decays, each generator produces about 4 fewer watts than it did the year before. The cameras were shut off in 1990 to conserve power. Their last act, before going dark forever, was to take a series of photographs of the solar system from a distance of about 40 astronomical units, a final backward glance at the family of planets the spacecraft had spent 12 years passing through. In one of those photographs, at the request of Carl Sagan, the camera was pointed back toward the inner solar system and captured the Earth as a tiny point of light suspended in a band of scattered sunlight less than a pixel wide. Barely distinguishable from an imaging artifact, Sagan called it the pale blue dot. He wrote about it at length. He described how, from that distance, every human who had ever lived and died, every kingdom, every war, every grand achievement and personal tragedy had occurred on that pale blue point. It was the kind of image that changes how you think about scale. The cameras that took it were switched off shortly afterward. Various particle detectors and other systems followed over the decades, shut down one by one to preserve power for the instruments with the greatest scientific value for the interstellar mission. Each shutdown was a small, irreversible decision, a farewell to a piece of hardware that had survived against all probability, switched off not because it failed, but because the power to run it was needed elsewhere. By the time Voyager crossed the heliopause in 2012, only the 4 instruments described earlier were still alive. In 2017, NASA fired Voyager 1's trajectory correction thrusters for the first time since 1980, 37 years of dormancy. They were trying to extend the mission by reducing wear on the primary attitude control thrusters. The command was sent based on schematics written by engineers who were long retired, cross-referenced with decades-old operational documentation. Those thrusters, cold and idle for nearly 4 decades, fired correctly. In 2018 and 2019, other thruster sets were tested and confirmed still operational. In 2025, yet another successful thruster revival was reported. The spacecraft seems, improbably, to be more resilient than its own designers anticipated. In the spring of 2022, engineers noticed that Voyager 1 was sending back garbled telemetry data from its attitude articulation and control system, the computer that keeps the antenna pointed toward Earth. The data was not just incorrect, it was randomized. The words that came back made no sense. For months, the team at NASA's Jet Propulsion Laboratory worked to diagnose a problem from nearly 25 billion kilometers away, with a round-trip communication delay of nearly 2 days. If the antenna drifted off its pointing direction and was not corrected, the signal would be lost. Everything would be lost. What they eventually determined was that the attitude control system had, for reasons that were never fully explained, begun routing its health and status data through a different onboard computer, one that the team knew had failed years earlier. Every piece of status information was passing through that dead computer and being corrupted before transmission. The fix was conceptually simple: redirect the data flow back to the working computer. Executing that fix required sending a command to a machine operating in interstellar space, waiting 44 hours for the round trip, and hoping the spacecraft executed it correctly. One engineer called it the ultimate telesurgery. It worked. The data cleared. Communication was restored. The mission continued. There is something almost absurd about what Voyager has accomplished. These spacecraft were designed with computers that had less total memory than a basic calculator. Their transmitters produce about 23 watts of power, less than a refrigerator light bulb. By the time that signal reaches Earth across billions of miles of empty space, it is weakened to about 1/quintillionth of a watt, 1 followed by 15 zeros below the line. The faintest signal humanity routinely receives and decodes. The Deep Space Network, 3 massive antenna complexes in California, Spain, and Australia. Each dish 230 feet across listens for that whisper and pulls it from the background noise of the universe. The 3 sites are spaced around Earth's circumference so that as the Earth rotates, at least one of them always has a clear line of sight to wherever Voyager happens to be in the sky. Without that infrastructure, without those 3 stations and their continuous availability, none of the discoveries would exist. The signal and the listening are equally necessary. The numbers describing interstellar space are worth pausing on. The density of the interstellar medium in the local interstellar cloud, as measured by Voyager, is roughly 0.08 electrons per cubic centimeter. For comparison, the air you are breathing right now contains approximately 10 to the 19th power molecules per cubic centimeter, a 10, followed by 19 zeros. The interstellar medium is not just thin, it is incomprehensibly thin. More than 1 trillion times less dense than the best vacuum chambers on Earth can achieve. An astronaut floating in it would not experience a breeze. There is simply not enough material to exert any mechanical force on a human body. And yet there is enough, just enough to matter. Enough to exert pressure on the heliosphere across the vast surface area of the solar bubble. Enough to carry a magnetic field that compresses the heliosphere more than any model predicted. Enough to vibrate in response to pressure waves from a star billions of miles away, and to carry those vibrations to a pair of 30-foot antennas still listening after 50 years. The current power budget is approximately 249 watts. Everything: the instruments, the antenna, the heaters, the transmitter must run on less than what a standard incandescent light bulb requires. Engineers balance these loads every year. Instrument heaters will eventually have to be sacrificed, exposing the electronics to temperatures that may eventually cause them to fail. Sometime around 2030, the transmitter itself will no longer have enough power to send a signal home. Voyager 1 will still be moving at approximately 38,000 miles per hour. It will still be carrying its instruments and its golden record and its message from a civilization that built it. But we will no longer be able to hear it. The golden record deserves a moment here, because what it represents is different from what it is usually described as. Each Voyager spacecraft carries a 12-inch copper disc plated in gold, containing sounds and images assembled by a committee chaired by Carl Sagan. Greetings in 55 languages. The sound of a humpback whale, a human heartbeat, laughter, rain, surf, 90 minutes of music from cultures across the world, diagrams, and encoded images. Instructions for playing the record are etched on its surface in symbols intended to be readable by any intelligence familiar with basic physics. The record was assembled under the assumption that some intelligence, somewhere, might eventually intercept Voyager and find it. Sagan believed the universe might be populated enough that this was not entirely implausible. What is easy to miss is the context in which those records now exist. They are in interstellar space in the local interstellar cloud, in a region of the galaxy where no probe, no radio signal, no light from Earth has yet arrived. The nearest star, Proxima Centauri, is about 4¼ light-years away. Voyager will not reach it on its current trajectory. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of a dim star called Gliese 445 in the constellation Camelopardalis. That is not a close pass. 1.6 light-years is a vast distance, roughly 300,000 times the distance from Earth to our own star. The record will pass in the dark, silently, at an immense remove from anything that might find it. And yet, here is what stays with you about the record. It was assembled by a species that had never left its own solar system, sent on a spacecraft that its builders assumed would fall silent after 4 years, and is now traveling indefinitely through the interstellar medium carrying a message to nobody. The chances of recovery are essentially zero. The message may drift for billions of years before anything encounters it, and anything that encounters it at that point will likely be as unrecognizable to us as we would be to Australopithecus. But Sagan wanted to send it anyway. He wanted to say, we were here and we were curious. And in the year 2026, that record is in interstellar space, still moving. And the spacecraft carrying it is still transmitting data that is rewriting what we know about the galaxy it is traveling through. The scientific community is preparing slowly for that silence. New Horizons, the spacecraft that flew past Pluto in 2015, is currently heading outward and is expected to reach the heliopause sometime around 2030. Its power budget is unlikely to carry its instruments much beyond the late 2030s. But even a few years of in situ measurements from a third crossing direction would add a third data point to the 2 we currently have. 3 data points do not constitute a map of the heliopause, a boundary that spans the entire sky across billions of square miles of space, but they are more than 2. And the difference between 2 and 3 can be enough to distinguish between models that 2 data points alone cannot separate. Beyond New Horizons, NASA is developing a concept called the Interstellar Probe, a dedicated mission designed from the outset to cross the heliopause and travel to distances of 500 or even 1,000 astronomical units. Unlike Voyager, which reached the interstellar medium as an incidental consequence of a planetary exploration trajectory, the interstellar probe would be specifically aimed at the interstellar medium from the start, carrying modern instruments optimized for the measurements that Voyager has shown to be most valuable: plasma density with continuous precision, magnetic field strength across multiple directions simultaneously, cosmic ray intensity across a much wider energy range, and neutral atom detection to map the heliopause boundary remotely as it travels through it. The mission concept envisions using a Jupiter gravity assist to reach velocities significantly faster than Voyager, shortening the journey to the heliopause from decades to roughly 15 to 20 years. If it is funded and launched in the next decade, its primary science from deep interstellar space would begin arriving in the 2080s. The researchers designing it today will likely not be alive to read those results. The scientists who will publish the core science from that mission are probably in their teens right now, or younger. That is the arithmetic of this kind of distance. You plant seeds for people you will never meet. What Voyager has left behind and will continue to leave behind for the next few years while its transmitter still has power is the first direct sampling of the very local interstellar medium across an extended baseline of roughly 40 to 50 astronomical units of interstellar space. A tiny fraction of the distance to the nearest star, a minuscule sample of the interstellar medium that fills the galaxy. But it is the only sample any instrument has ever taken from inside it. And it has already overturned the models, revealed unexpected structures, detected a continuous plasma hum, found a magnetic field twice as strong as predicted, and produced a 2-year-old anomaly that may carry the imprint of another star's ancient environment drifting through the space between ours. When you trace what Voyager 1 has actually been doing since 2012, not leaving the solar system, but sampling the local interstellar cloud in which our solar system currently travels, the significance becomes something different from the headline version. The headline version is about a spacecraft escaping. The real version is about a spacecraft arriving somewhere nobody had ever been and finding that what was supposed to be empty space between the stars is, instead, a complex, structured, magnetically rich, plasma-threaded environment that we had been wrong about in almost every particular we had estimated. Consider what we still do not know. The heliopause crosses the entire sky, above and below the plane of the solar system, ahead of the direction of the stellar motion and behind it, through every point of the compass imaginable. Voyager 1 and Voyager 2 have crossed 2 narrow slits in that boundary, one near the nose, one near the flank. They have given us 2 data points in a measurement space that requires dozens of them to characterize properly. What is the heliopause like above and below the plane? How does it behave in the tail region, where the solar wind streams away behind the stellar direction of motion? Does the boundary close properly there, or does it trail off into an elongated structure? Is the magnetic anomaly that started in 2020 a local pocket, or does it extend for thousands of astronomical units? How does the density of the local interstellar cloud vary across the 30 light-years it spans? All of these questions are currently unanswerable. We have 2 pinholes in a boundary that wraps the entire sky, and from those 2 pinholes we are trying to deduce the shape, composition, and structure of the entire surrounding space. There is also the question of what the heliosphere actually looks like from outside. Some current models, incorporating both Voyager data and IBEX observations, suggest it is not a rounded bubble at all. It may be something closer to a crescent blunt at the front where the stellar wind presses hardest against the interstellar medium and trailing an elongated structure downstream. Other models suggest a comet-like shape with a long tail. The IBEX ribbon, and the way its arc traces across the sky, implies that the local interstellar magnetic field is oriented at an angle that constrains the downstream shape significantly. Whether the heliosphere is teardrop-shaped, crescent-shaped, something stranger, or something that defies any simple geometric analogy, is a question that Voyager's 2 crossing points alone cannot resolve. We need crossings at the poles. We need a crossing in the tail. We need a mission specifically designed to explore the heliosphere's shape systematically, rather than inferring it from 2 machines that crossed the boundary at angles determined by where the planets happened to be in 1977. And yet, from those 2 crossing points, from 50 years of continuous operation, from instruments that were never designed for this purpose and should by any reasonable expectation have stopped working decades ago, we have already rewritten the textbooks. The interstellar medium does not hum for everyone who passes through it. It hummed for Voyager 1 because Voyager 1 was there, listening, with 2 30-foot antennas and an instrument built half a century ago that turned out to be perfectly suited for a purpose nobody anticipated when it was designed. When that happens, the very local interstellar medium will go back to being known only by inference, by models, by remote observation until New Horizons gets there, or the interstellar probe, or whatever comes after that. Until then, Voyager 1 is still the only instrument humanity has ever placed on the other side of the solar wind. Tonight, it is still there, still moving, still transmitting. In November of this year, it will pass the milestone of being 1 full light day from Earth so far away that the light leaving Earth right now will not reach it for 24 hours. And it is still less than 1/100th of the distance to the nearest star. The interstellar medium through which it travels stretches on, essentially forever, in every direction beyond it. We have sampled a thin thread of it across a distance that would be unmeasurable by any human standard of scale, and from that thread, what we have learned has already rewritten what we knew. Thank you for being here tonight. If this journey left you with more questions than it started with, if that feeling of how much we still do not know feels like something worth sitting with, then subscribe and stay with us. Every video on this channel starts from exactly that place. We will see you in the next one.